Okay, so sample exam 1. Look at number 1, they give us a piecewise function. And ultimately the pieces are x squared plus bx and 5 sine pi over 2x. And this is x less than or equal to 5, and this is x greater than 5. And ultimately the question is, with this function, b is some constant, and it says if f is a continuous function, then what is the value of b? So bottom line is, in terms of categories, this is just a continuity at a point problem. And what do we know about continuity at a point? Do the slopes have to be the same? Yeah, just the y values have to be the same. They have to go to the same point. So we don't have, this has nothing to do with derivatives then, does it? Okay, all we need to worry about is, are the y values the same at these points? Well, ultimately the y value at this one we can find because we can put a 5 into this one. Okay? And if we did that, we'd get 5 sine of 5 pi over 2. And sine of 5 pi over 2, keep in mind, is just the same as pi over 2. Sine of pi over 2 is 1, so we ultimately get 5. So that means that we want x squared plus bx to be equal to 5. But what's the problem with this sentence that we have here? It's got two variables. However, we want this to be true when x equals what? That has to be true when x equals 5. We want it to go through the point 5, 5, true? So now we don't have two variables and we can solve. So ultimately we get 5b here and we get negative 20 over here. Subtract 25 from both sides. So ultimately we get b equals negative 4. One thing as we do this is I'd always write this down in my notes here as we look at these problems together. The stuff that I write on the side here, because at some point you need to start getting kind of a catalog of information in your mind about what kind of problems that you are having trouble with and what kind you're not. Okay? So if you're having trouble with the continuity at a point problem, those are the kind of more problems that we want to do, try to find more of them, etc. So kind of start to categorize what type of problem that we're doing so that we know exactly what our strengths and weaknesses are as we go. Okay? So keep track of which ones you're getting right, which ones you're getting wrong, what category they might be from. I'll try to remember to put the category on there each time, and if I forget, you can remind me. What else? 1 through 7. Alright. Number 3, we have, says we have forest. It's in the shape of a rectangle, and it's 5 miles long, 3 miles wide, and the density of the trees at a distance of x miles from the 5 mile side. So keep in mind, we're looking at a rectangle. We have the 5 mile side. I'm going to draw it like this. We have this as the 3 mile side. True? Okay, and so we're looking at the density here is this rho of x function. Rho being a Greek letter, of course. And the question is, which expression gives the number of trees in the forest? Now keep in mind that this rho of x function is measured in trees per mile squared. True? So it's in trees per mile squared. Keep that in mind. All right. And ultimately, if we were to draw a picture of this rho function, this density function, or whatever it may look like, if we had trees per mile squared versus miles, because again, x, keep in mind, is miles. If I just straight up found the area under that curve, would that give me trees? Yeah. It still give me trees what? Per mile. It would give me trees per mile. So that's just the straight up integral here is not going to work then, is it? If I go integral from 0 to 3 of rho of x dx, that's not going to give me trees. Okay? And again, the unit analysis here is the important part because we have to be able to make sure that we set up the integral properly so that the units work out. Because if they don't work out, then it's not the right integral. Okay? So the question is, if it's trees per mile that we get, how could we remedy that? We need to get rid of those miles, don't we? So somehow we have to introduce another variable here in terms of miles. Okay? And ultimately, in the forest here that we have, again, keep in mind if we're doing the density as we go from left to right here, we're on the right track by saying rho of x here. But again, just doing rho of x will give us trees per mile. We don't want trees per mile. So we have to essentially multiply by another something miles. And what is the other something miles we have in this problem? That's the 5, isn't it? Okay. So if we did this for a 5 mile stretch, and we can put it right in with rho of x, or we can put it on the outside because it's just a constant here. But ultimately it's 5 miles that we're multiplying by. And so with that said, now if we do the integral, we'd have trees per mile times 5 miles would give us trees. So with that would be number what? Letter C? Ultimately this would be, it's called an integral as an accumulator. Keep in mind that, that this is a topic that we've just kind of started scratching the surface of. So if you didn't get that right, I wouldn't be surprised at this point. So we, in chapter 6 and 7, we do quite a bit more of this integral as an accumulator type of problem. Once you do a few, it's really not that difficult, but you just gotta see it for the, like I said, my main thing to look at that on a problem like this is make sure the units work when you set that integral up.
Normally would it just work because like if you have like miles per hour and then hours per mile,
Then you just do the straight up integral, yeah.
But is it because it's miles squared?
It's because it's trees per mile squared versus miles, which means that it's trees per mile squared versus miles. So that's why the units don't work out. If I just did the area, it'd be trees per mile squared times miles, which would give me trees per mile. But I don't want trees per mile, I want trees. So somehow I need to get rid of that other miles, which ultimately introduces that other 5 they gave us. Good question. Like I said, we'll do quite a few more of those as we proceed forward here from here on out. What else? 4. And 4, we got e to the sine x is our function. And we have, question is how many zeros does the derivative have? Well, if we look at the derivative here, the derivative is going to be itself times the derivative of the argument. So e to the sine x times cosine x. The question is how many zeros is it going to have on the closed interval 0 to 2, or 0 to 2 pi. So keep in mind that if we want to know the zeros of this, ultimately we have a product here, don't we? Yeah. So if we use the zero product property, that means e to the sine x would have to equal 0. Or cosine x would have to equal 0. Well, ultimately, what do we know about e to the sine x? No matter what I put into the e function, I'm raising it to a power, right? So does the e function ever equal 0? Nope. No. So this doesn't ever equal 0. What about cosine? How many times does cosine equal 0 between 0 and 2 pi? Cosine looks like this, doesn't it? So ultimately, how many? 2. Alright. So ultimately, category-wise, it would just be application of derivative. And also some algebra too as well, right? And make sure we know what those functions look like. So again, a non-calculator problem, you absolutely need to know something about e to the sine x and cosine x without being able to graph it. Questions on that one? What else? 7, we have just a derivative at a point problem. We got the f of x function of 4 sine x plus 2. And we want to know what's the derivative at 0. So again, this is the derivative at a point. That'd be the category. And ultimately, the derivative here, I would first rewrite this in power form if I were you. That way we can use the generalized power rule here, recognizing the power function is the outside function, so the derivative would be 1/2 times 4 sine x plus 2 times the derivative of 4 sine x plus 2, which ultimately would be 4 cosine x. Questions on the derivative part?
And multiply to get dropped, so that's equal to 4.
Actually, you know what I did forget is I need that though. Sorry. So I'll multiply what now?
The multiplier on 4, that comes out when you do the derivative of sine x. That's equal.
Well, yeah, ultimately the derivative of 4 sine x would be 4 cosine x. Because it's constant multiple. So, alright, then from there let's evaluate here. We got 1/2 here, and in the parentheses we have 2. Because sine of 0 is 0. So we'd have a 2 in the parentheses. And over here we'd have just a 4 because cosine of 0 is 1. And if we do 2 to the negative 1/2, that'd be 1 over 2 to the 1/2. It'd be 1 over square root of 2 times 1/2 times 4. So So ultimately we get 2 over radical 2. If you look at 2 over radical 2, is that an option? No. But ultimately we can rationalize that and get 2 radical 2 over 2, which is ultimately equal to radical 2, which corresponds with letter E. Alright, what else? Anything else in the 1 through 7? Alright, well, let's carry on then. Number 8 through 14 are the following. Got 8 is B, 9 is C, 10 is D, 11 is B, 12 is A, 13 is E, and 14 is A. How about from that group?
8.
Yeah, number 8, this one is kind of similar to that forest problem that we had a minute ago here. We have an integral that we have to interpret here. And if we do our 10,000 to 30,000 and r of x all squared dx, one of the things that based on the problems that we've been doing recently, okay, we might recognize this. Isn't this a pi r squared h kind of situation? Doesn't that look like the integrals we've been setting up for the volumes? True? Alright, and so keep in mind here that that our the function that we have here is this r function is radius, okay? Alright, and the this x is measured in feet, okay? And we have our ultimately we have our radius squared, okay, times pi. We're finding a volume essentially. So if you look at the choices we have here, this is the first one is the amount of water in square feet that the pipe can hold. Now keep in mind that if we're talking about an amount of water that the pipe can hold, are we going to be talking about square feet? Think about what units it's going to have to be out of this. This should be cubic, shouldn't it? I mean, we're just going to recognize here that this is a volume that we're calculating because we've done a lot of volume problems so far. We're going to do even more in the future here shortly, but bottom line is recognize this is a volume problem. Okay, we know that whatever we say, it better be something in cubic feet here. So ultimately, if that A means A is out. What about letter B? The amount of water in cubic feet that the pipe can hold in the section from 10,000 to 30,000? Does that seem reasonable at this point? Yeah, it seems pretty reasonable because, and then how about part C says the amount of water in cubic feet flowing through the pipe? Okay. At least the cubic feet part keeps it in the ball game, right? Okay. Unit-wise. How about part D, the amount of water in cubic feet in any 20,000 foot section? Okay. And with this, if I use specifically 10,000 and 30,000, would that be good for any section of the pipe? No. Okay, it could be different in different parts of the pipe, so that's definitely out. And then how about part E, the rate at which water flows? Okay. This is not a rate, it's a volume, right? So that one's out too. So the bottom line is we got to figure out, is it B or is it C? Okay. Ultimately, keeping in mind that if we look at part B again is going to be, we're talking about the R value here being the radius of the pipe. Okay. So ultimately, is it the radius of the water that we're calculating here are we using, or is it the pipe? I mean, when the water's flowing through the pipe, does the pipe have to be completely full of water at all times?
No.
So ultimately, is this about the pipe or is it about the water? It's about the pipe. Right? So therefore, which one does it have to be? It's got to be letter B. Okay? It's not about the water, it's about the pipe. Keep in mind, when water flows through a pipe, the pipe isn't 100% full all the time, is it? Okay. So keep in mind that, again, R value is the giveaway because they told us it's the radius of the pipe. It's not the radius of the water. So therefore, we're talking about the pipe. We want the pipe volume, not the water volume. Okay. All right. So ultimately, again, this would probably, I guess, would be a volume problem, but also integral as an accumulator.
Wait, what would it be?
Okay, what else? 8 through 14. For one more, Taylor. On 10, we have the question here with number 10. We got a velocity graph here, right? So this is the velocity. At which of the points is the speed the greatest? Okay. Well, ultimately the velocity is the greatest at B. True? Remember, this is the velocity, so its values are the velocity values. The velocity value would be the biggest at B. But what about at D? Remember, the speed is the absolute value, so wouldn't the velocity would here be negative something bigger than B, wouldn't it? So therefore, ultimately, the speed would be the greatest at point D, wouldn't it? So, A is not a candidate because it's less than B. C and E are, you know, virtually zero. Well, C is zero. E is close to zero. But ultimately, D would have the biggest speed. They would have the lowest numerical value for velocity, but ultimately that would translate to the biggest speed because the absolute value of the velocity is the speed. All right, we'll do more of those at another time. What I want you to do, besides study for your test here, is start working on the calculator part of sample exam 1, so 29 through 45. And like I said, as we go, anytime we have time, we'll carry on through these problems. So we'll leave off with number 10 for today.
Calculator or non-calculator?
Calculator.